Okay, so here you have a question from the chapter States of Matter. Here we're dealing with a question which says that you have two different gases, right? So for 10 minutes each at 0 degrees Celsius, from two identical holes, nitrogen and an unknown gas are leaked into a common vessel of 4-liter capacity. Okay, so your volume is given to you as 4 liters. Time is given to you as 10 minutes for both the gases. Temperature is given to you as 0 degrees Celsius, which is nothing but 273 Kelvin. So much information only in a single sentence, right? Okay. The resulting pressure in the vessel is 2.8 atm. So pressure is going to be 2.8 atmospheres. Then what do you have? And the mixture contains 0.4 moles of nitrogen. So number of moles of nitrogen is going to be 0.4. Okay. What is the molar mass of the unknown gas? Okay, so let's say this unknown gas is X. They want you to find out the molar mass of X. Okay, see, you are talking about some leakage from a very tiny hole into a common area. You're talking about diffusion of gases. So here, basically, what you need to apply is going to be Graham's law. And the form of Graham's law that we're going to deal with is going to be this. Number of moles of N2 divided by number of moles of, let's say, X, as we have assumed, is equal to under root of molar mass of X divided by molar mass of N2. Correct? This is the form of the law that we're going to adapt. Right? Why am I using this? Because see, they are talking about the same time period, right? So that time became a constant. So that is one very big advantage I have, which makes the question very simple for me. Okay? This is the law that I'm going to use. So I basically need to find out number of moles of X, because if you see, they've given us the number of moles of N2. You know the molar mass of N2. Okay. You have to find out this. So basically you just need this. Okay. How will you do that? We will find out the total number of moles, subtract number of moles of N2, and we will get number of moles of X, right? So you have all this data given to you. So let's get started. We will use PV is equal to nRT, ideal gas equation. You have to find out number of moles, that is N. So you will have PV by RT. Okay, you have to write the value of R. R is going to be 0.0821, which is nothing but 1 by 12 liter atmosphere per mole Kelvin. This is the sort of value that R will take. So let's substitute everything. So your N is going to be P, which is 2.8 atm, multiplied by V, which is 4 liters, divided by R, which is 1 by 12 liter atmosphere per mole Kelvin. And your temperature is going to be 273 Kelvin. Okay, now here what I will do is I need to cancel things out. So I need to make some approximations because this does not look like a very simple calculation. So I am making this approximation. I'm saying 273 is approximately equal to 272. No harm, no foul. Okay, so here cancel this out with 4. You get 6 and you get 8, right? Now you basically have 68 by 12, right? I'm writing this entire thing as one thing. So that's nothing but 60 by 12 plus 8 by 12. 60 by 12 is 5. This much you know. 8 by 12 is nothing but 2 by 3. 2 by 3 is nothing but 67% or 0.67. Right. So basically this will be 5 plus 0.67. That's nothing but 5.67. Correct? So we'll cancel it out. This will go once. This will go 5.67 times. Okay. Very precise, but you know that it didn't involve too many calculations so far. Okay, so now what do you have? You have 2.8 divided by 5.67. So you do 2.8 into 2. What do you get? You get 5.6. So cancel this out once, cancel this out twice. Your N comes out to be 1 by 2, which is nothing but 0.5 moles. Okay, so your total number of moles is going to be 0.5. Your number of moles of nitrogen plus number of moles of X is equal to 0.5. This is given to you as 0.4. So your number of moles of X is going to be 0.5 minus 0.4, which is nothing but 0.1 moles. Substitute everything that we know into this relationship. So you get number of moles of N2 divided by number of moles of X is equal to under root of molar mass of X divided by molar mass of N2. So this is coming out to be 0.4 by 0.1 is equal to under root of molar mass of X divided by molar mass of nitrogen is going to be what? 2 into 14, nothing but 28 gram per mole. So what you have is basically 4 is equal to under root of mx by 28. I will simplify this. I'll square it on both sides. You have 16 is equal to mx by 28. So your mx is going to be equal to 28 into 16. Okay, so now what do we have? We have 28 into 16. When you simplify that, you get 280 plus 140 plus 28. So you write 8, you write 12 and 2, 14, and you write 4. So this is coming out to be 448 gram per mole. This is the molar mass of the unknown gas X. It's a pretty heavy gas. So your right answer is option A, 448 gram per mole. Okay, so here they're saying which of the following is a redox reaction. Okay, so basically for it to be a redox reaction, you need to ensure that there is reduction happening and there's oxidation happening. Both of these need to happen in the same reaction. Only then can you call it a redox reaction, right? Simple. Let's look for it. So you have option A, magnesium carbonate is giving you magnesium oxide plus carbon dioxide. Here you know magnesium is in +2 oxidation state, carbon is in +4 oxidation state, oxygen is in -2 oxidation state, right? So what happens in MgO? Let's see, you have magnesium still in +2 oxidation state, oxygen in -2, carbon in +4, oxygen in -2. Correct. So basically whatever was the oxidation state before the reaction, even after the reaction, it's the same. So on the reactant side and on the product side, you have the same oxidation states. So this is not a redox reaction. Okay. In fact, this is going to be a decomposition reaction. Cool. Next, you have option B. And here they're saying that you have BaO2 plus H2SO4 gives you BaSO4 plus H2O2. Okay. Barium you know is in +2 oxidation state, right? And here oxygen is not in its usual -2 oxidation state, right? Let's find out. You have +2 plus 2x is equal to 0. So which means x plus 1 is equal to 0. So you have x is equal to -1. So oxygen is in its -1 oxidation state, as we generally see in peroxide. So this is barium peroxide. This will react with H2SO4. So H2SO4 hydrogen is in +1 oxidation state. Sulfur is going to be in, let's say, in Y oxidation state. This is in -2. You have to find out why, right? So what happens in sulfate? How do you find out? So you have 2 plus Y -8 is equal to 0. So you have y -6 is equal to 0. You have y is equal to +6. Right? So this is going to be +6. I'll just write it here. Then you have barium sulfate. So barium is still in +2. Sulfur is still in +6. Oxygen is still in -2. Okay. H2O2. Hydrogen is still in +1. Oxygen is still in -2. So you can see and you can compare that the oxidation state of every single element is the same as it was before the reaction. So before and after the reaction, 1 second, this is going to be -1. Okay. So your oxygen still has a peroxide, it still has an oxide, barium is still in +2, hydrogen is still in +1. So everything more or less has remained the same. Okay. This is not a redox reaction. Then you have option C. AS2S3 plus HNO3 is giving you. So here you have option C, which is saying AS2S3 plus HNO3 plus H2O is giving you H3ASO4 plus H2SO4 plus NO, right? So let's see. So here you have arsenic and you have sulfur. Now you can see that by cross multiplication you'll get their oxidation states. So sulfur will be in -2, arsenic will be in +3. Correct? Then you have HNO3. So here you will have hydrogen in +1, oxygen in -2, and nitrogen in +5 oxidation state. What about H2O? Here you have hydrogen in +1, oxygen in -2. Correct? Now come to H3ASO4. Okay, so here you will have hydrogen in +1 oxidation state, oxygen in -2 oxidation state. We have to find out for arsenic, right? So let's call it X. So you have +3 plus X minus 8 is equal to 0. So you have X minus 5 is equal to 0. Okay, so which means you have X is equal to +5. Right, so arsenic is in +5 oxidation state. Great. What else do we have? We have H2SO4. So for H2SO4, we just calculated here, right? We calculated right here, so let's write that down. You have +1, +6 and -2. These are your oxidation states of the respective elements hydrogen, sulfur and oxygen. Then you have NO. So this is pretty simple. This will be -2, this will be +2. Okay, so now you can see there is quite a lot of change in oxidation state that's happening. So you can see arsenic went from +3 to +5. First of all, that is oxidation. Okay, then you have sulfur, which went from -2 to +6. Okay, so you have sulfur which went from -2, and drawing lines is kind of messy here, so I'm just going to circle it. So sulfur went from -2 to +6, right? So this is what, this is also oxidation. Okay, this is also oxidation. Then you have nitrogen, which went from +5 to +2. This is reduction, correct? What else do we have? Okay, oxygen and hydrogen retained their oxidation state, so that's fine. But you can see that there is ample reduction in oxidation happening here, which means this qualifies to be a redox reaction. So option D, none of the above, is automatically ignored, right? The correct answer to this question is going to be option C. So here they're asking you to consider the following reaction. You have copper plus 4HNO3 dilute will give you copper nitrate plus 2H2O plus 2NO. Fine. Which of the following statement is correct? We need to find out the correct statement. So we'll read the statement, we'll mark true or false, and whatever is true is going to be the right answer to this question. So let's see. First you have HNO3 is the oxidant, whereas Cu is the reductant. Okay. See, before we actually look at all the statements, we'll have to go ahead and we'll have to calculate the oxidation states for each of them. We'll have to figure out what is getting oxidized, what is getting reduced, and then come back to the options, right? So let's do that first and then we'll come back to the options. Okay, so here you have copper, which is in 0 oxidation state. What about HNO3? Here you will have nitrogen in +5 and hydrogen, oxygen in their normal +1, -2. So that's fine. Then here on your product side, you have copper in +2 oxidation state, because you can see copper nitrate. Nitrate ion exists like this, correct? So if you have this taken twice, which means the charge contributed due to this is 2-, okay? And that charge is being nullified by copper. So copper has a charge of 2+, which means its oxidation state is +2, okay? So this is understood. Nitrogen is as usual +5 here also. Then you have 2H2O, where needless to say hydrogen is in +1, oxygen is in -2. So this is fine. And then you have NO. So what happens in NO? You have nitrogen in +2, oxygen in -2. Okay, so this is all sorted. Now let's see. What do you see? What is happening? You can see that copper is getting oxidized. It's going from 0 to +2. So copper is getting oxidized, which means copper is going to be the reducing agent or the reductant, right? So that leaves us with HNO3. HNO3 is going to be the oxidant or the oxidizing agent, right? Alternatively, you can see that in HNO3, nitrogen went from +5 to +2, correct? So nitrogen went from +5 to +2, which means it is getting reduced and helping copper get oxidized. So HNO3 is going to be the oxidizing agent or the oxidant here. Fine. So now let's check the options. You have option A, HNO3 is the oxidant, whereas copper is the reductant. This is absolutely true. This is what we have written. Then you have option B, copper is the oxidant, whereas H2O is the reductant. That's not true, okay, because first of all, copper is the reductant and water, right? Water on the reactant side, water is not featuring at all. Okay, they said dilute HNO3, but they have not featured water in the reaction. So we can't include that in our discussion, right? So H2O as the reductant is not okay. And copper is also not the oxidant, it's the reductant. Then you have copper is the oxidant, whereas HNO3 is the reductant. This is false. Sorry, this is going to be false, not true. Sorry. Okay. Now see, from this question, one thing I want you to take away is that wherever you have dilute HNO3, right? Almost everywhere in inorganic chemistry, you can say that if you have dilute HNO3, it's going to be the oxidizing agent. It's a very good oxidizing agent. Why is that so? Because you have nitrogen in the +5 oxidation state. That is its highest oxidation state, right? No matter what you're putting with HNO3, nitrogen cannot have a higher oxidation state, can't go to +6, +7, which means nitrogen will always have to go lower in its oxidation state, which means HNO3 or the nitrogen in HNO3 is always going to get reduced. What does it mean? That the corresponding species is going to get oxidized? Yes? Okay, so HNO3 is a good oxidizing agent. That is what I think you need to take away from this question, right? The correct answer here is going to be option A, that HNO3 is the oxidant, whereas copper is the reductant. Alright, so here you have for 3ClO minus aqueous giving you ClO3 minus aqueous plus 2Cl minus aqueous. Identify the type of reaction, right? So options are decomposition reaction, disproportionation reaction, reduction reaction, oxidation reaction. These are your options. So what we'll do is we'll find out the oxidation state of everything, and then we'll see what sort of a reaction this actually is, right? So let's see. You have ClO minus, right? ClO minus is what we have. So basically oxygen as usual is going to be in -2 oxidation states. You have X minus 2 is equal to -1. So which means X is going to be equal to +1. So chlorine is in +1 oxidation state. Here you can see it's going to be in -1 oxidation state because it says Cl minus, chloride ion. So -1 oxidation state. Now let's come to ClO3 minus. So you have Y minus 2 into 3, so -6 is equal to -1. So which means Y is going to be equal to +5, right? So here I'll write +5. Okay, so all of this is sorted. You have all the oxidation states. Now you can see that chlorine here, right? Chlorine is going from +1 to +5 and +1 to -1 simultaneously. So +1 to +5 is oxidation, +1 to -1 is reduction. So chlorine is undergoing reduction and oxidation simultaneously in the same reaction, in the same step. What is this sort of a reaction called? See, this sort of a reaction is called disproportionation reaction. Correct? This is called a disproportionation reaction, which means option B is the right answer to this question. So here they're asking you to find out which of the following can function as an oxidizing as well as a reducing agent. Okay, so basically you need whatever, okay, you have molecules here. So whatever molecule you take has to be able to oxidize something, and it should also be able to reduce something else, right? That should be the property of that molecule. How do you go ahead with this question? Basically, you need to ensure that whatever elements you have in that molecule, right, at least one of them, right, that one element should be in an intermediate oxidation state. You don't want it to be in the highest possible oxidation state or in the lowest possible oxidation state. Basically, it should be at an intermediate oxidation state such that it can get oxidized and act as a reducing agent, or it can get reduced and act as an oxidizing agent. You need this fundamental idea. Okay, so let's see. You have option A, H2S. So here hydrogen, you know, is going to be in +1 oxidation state. Sulfur is in -2 oxidation state. Okay, sulfur, the least oxidation state that sulfur can show is going to be -2, right? So here it is in the least possible oxidation state. So it is not going to, you know, go any lower. It can go higher. Yes, agreed. Sulfur can go higher. It can show +4, +6. It can show all of this. But it cannot go lower than -2. Okay, so H2S is not going to act as both oxidizing and reducing agent. Hence, A is discarded. Option B, H2SO4. You have hydrogen as usual in +1, sulfur in +6, oxygen in -2, right? So here sulfur is in the highest possible oxidation state, which is +6, right? It cannot go any higher than this. Lower, yes, it can. So it can get reduced. It can act as an oxidizing agent, but it cannot act as a reducing agent, right? So this can also be discarded. Then you have H2O2. Okay, now you have option C, H2O2, hydrogen peroxide. The name itself is suggesting that hydrogen will of course be in +1, but oxygen has a peroxide bond here, so oxygen will be in its -1 oxidation state, right? Very important. This is what you need to keep in mind here in case of H2O2. Okay, so now what happens, you know that oxygen the highest oxidation state is the superoxide state, or even the elemental state, right? 0. Okay, and in the lowest oxidation state that it can go is in the oxide form, O2 minus, right? So here it is in -1 state, which is technically what? It's an intermediate oxidation state. So H2O2 can act as both an oxidizing agent as well as a reducing agent. It can function as both. So this statement, so H2O2 is going to be the correct choice. Then you have SO3, in which case you have sulfur in +6 form and oxygen in -2 form. So sulfur is in the highest possible oxidation state. Oxygen is in the lowest possible oxidation state. So it's not possible for SO3 to act as both oxidizing and reducing agent. Hence, this can be discarded. So the correct answer to this question is going to be option C, hydrogen peroxide.